This tutorial demonstrates the shear moment diagrams in SimXpert. In this tutorial, you will learn how to create monitor points at the split positions and from the monitor points create shear moment diagrams. In SimXpert, import a shaft parasolid. The same origin is used in SimXpert as the CAD package it came from. Now first create the material property as well as the solid 3D property. Then create a solid mesh of 5 mm with the element type as quadratic. Tick parasolid assembly parameter and make sure the match parasolid faces is selected so that two nodes coincide with the adjacent solid bodies. Deselect the curvature check option, which in essence refines the mesh. Zoom into the left view where the bearing will be placed. Under the Assembly tab, select Rigid Body Element 2. Use Advanced Picking to highlight the nodes on the surface. Use the default settings and select OK. Select Geometry Wireframe and take note of the sophisticated setup the program has achieved. To attain the middle node, we can zoom in and right-click to go to Properties. Here we can copy the position of the middle node. Under Load and Boundary Conditions, select the General Constraint tab. Here we can constrain the middle node, but only in the Y and Z direction. So instead of trying to constrain every node, we first link all the nodes to the center node, and then we can constrain that single one. Repeat the same steps on the other side of the shaft, but this time let it be free to rotate about the Y and Z axis. On the other side of the shaft, represent a pressure load in the Y direction from the pulley. For this tutorial, we used an applied load of 650 newtons and divided it by the area obtained in the statistics option to arrive at our pressure load. Now calculate the pressure load experienced with a force of 300 newtons on the cutting disc side in the Z direction. Turn on the rendering option to view the pressure loads. Now create a new Nastran job with a linear static analysis solution type. Go to Output Requests and then Nodal Output Requests, and then select Grid Point Force Balance Output Request. Run the simulation and attach the results. View the deformation and fringe plots to gain a better understanding of what is physically being represented in this finite element model. Verify whether the results make sense or not. Show all the geometry, hide the loads and boundaries, and select the left view. We will now create monitor points. To do this, select Shear and Moment Diagrams under the Results tab. Navigate to the Monitor Points tab and select Interface Loads. Select the Nodes target. Use the Advanced Picking tool to select the nodes in the plane of the monitor point. View it in Geometry Wireframe while also hiding the finite elements. Select the Elements target. Select the left view and view the finite elements. Click and drag to cover all the elements needed in that plane. Right-click in the toolbar space and click Tools. We can use the Statistics tool to determine the location of the split plane. You do this by selecting a node in the split plane and selecting the x-coordinate in the information given. Now we can enter our information into our location space and select our bending axes. Click Apply to confirm our monitor point. Follow the same procedure for the rest of the split planes. To recap, we will now show you how to create a monitor point at the last split plane. For this tutorial, we choose to pick the nodes and elements on the left-hand side. When all the split planes are finished, go to Monitor Point Groups and select Interface Loads. Click all 7 monitor points. Remember, the order is very important. Navigate to the Shear Moments Diagrams tab. Under the Display Attributes, deselect the moment components. Under the Plot Data tab, select Interface Loads. Under Target tab, select Monitor Point Groups and click Update. Under Windows, select Tile and view the shaft in isometric view. Comparing the FEA and hand calculation results, we can see that they correlate well. The forces in hand calculations are applied over an infinitely small length of the shaft, compared to a finite length of the bearing. That is why the FEA results do not have perfect straight lines, where the reaction forces are applied. This concludes a shear moment diagram tutorial. This tutorial was proudly brought to you by Tech, engineering technology for better business.